When NASA issues a geomagnetic storm watch, it can sound like something distant and abstract, the kind of warning that belongs to scientists and satellite operators rather than ordinary life. But a watch is not issued for drama. It is issued because the sun has done something measurable, something that can be tracked across space, and something that has a history of turning invisible physics into very real disruptions. To understand what breaks first, you have to picture the chain of events step by step from the moment the warning appears on a screen to the moment small everyday systems begin to behave strangely. It does not begin with a blackout. It begins with timing, with signals with the most delicate parts of the technological world, the ones that rely on the Earth's upper atmosphere remaining calm and predictable. A geomagnetic storm is in the simplest sense a storm in the space environment around Earth. It is driven by the solar wind and during stronger events by a coronal mass ejection, a vast cloud of charged particles and magnetic field that has been thrown outward from the sun. That cloud travels for days, sometimes faster, sometimes slower, and when it arrives it does not crash into the ground like a physical object. It presses against Earth's magnetic shield, the magnetosphere, and if the magnetic orientation is favourable for coupling energy, pours into the system. The magnetosphere compresses and ripples, currents intensify in space, and the upper atmosphere, the ionosphere, becomes disturbed. That is where the first breakages begin, because modern civilization depends on radio waves passing through that region as if it were steady glass, and on satellites moving through it as if it were thin, quiet air. During a storm, it becomes neither. It becomes a restless, shifting medium full of irregularities and sudden changes in density and charge. The earliest impacts are often felt in communications that rely on the ionosphere. High-frequency radio, the kind used for long-distance communication by aviation and maritime services, can fade, distort, or become unreliable when the ionosphere is disturbed. Signals that normally skip across the horizon can be absorbed or scattered. In practical terms, this is not the cinematic failure of all communication at once. It is patchy loss, sudden noise, unpredictable quality. A message that would normally be clear becomes faint. A frequency that worked an hour ago stops working, and the operators move to another, and then another. It is a reminder that there is still a layer of the planet we do not control, a layer that sits between us and space, and that can change with solar weather, the way the lower atmosphere changes with earthly storms. Alongside that, the next thing to wobble is navigation, especially satellite-based navigation. GPS and other global navigation satellite systems rely on timing signals travelling from satellites to receivers on the ground. The receiver solves for position by measuring how long the signal took to arrive, and it can do this only if the timing is stable and the signal path is well understood. The ionosphere is part of that path. During geomagnetic storms, the ionosphere can develop regions of enhanced density and turbulence which change the speed and path of radio waves. This can introduce errors, sometimes small, sometimes large, and it can cause scintillation, a rapid flickering of the signal, similar to how stars twinkle when the atmosphere is turbulent. To a receiver, scintillation can look like the signal is fading in and out or jumping in phase. In everyday life, this might mean a navigation app that becomes less accurate than usual, or a receiver that takes longer to lock. In specialized applications, it can be more serious. Aviation procedures, precision agriculture, surveying shipping, emergency response, and any system that relies on high-precision positioning can see performance degrade. The first thing that breaks is not the map itself, it is the confidence that the map is right. And in a world increasingly built on automated decisions, confidence is a quiet pillar. When it cracks, the system becomes cautious, slower, less efficient, and sometimes it fails over to backups that are older, more expensive, and less precise. At the same time, satellites begin to notice the storm in another way. Storm-driven heating in the upper atmosphere can increase atmospheric density at altitudes where low Earth orbit satellites fly. Even though the air there is extremely thin, the difference matters. Increased density means increased drag. Increased drag means satellites lose altitude faster unless they compensate and their orbits become harder to predict. For large constellations, orbit maintenance is a constant task even on quiet days. During storm conditions, that task becomes more urgent. Operators may need to perform more maneuvers which consumes fuel or propellant, reducing satellite lifespan. In severe cases, satellites can experience attitude control issues, increased charging, and anomalies in electronics. Some satellites enter safe mode, temporarily shutting down non-essential functions to protect systems. From the ground, this can appear as brief outages. A service hiccups, a connection drops, a stream buffers. Most people will never connect that moment to the sun because the disruption is small and the explanation is far away. But it is still a first break, a small fracture in the space infrastructure that normally feels seamless. Another early casualty can be the precise timing that underlies communications networks and financial systems. GPS is not only about location, it is also a widely used source of timing. Many systems use the timing signals from satellites to synchronize their operations. When ionospheric disturbance affects signal quality, it can create challenges for receivers and in rare cases contribute to timing errors if not handled correctly. The systems that are well designed have redundancy and cross-checks. The systems that are not can become subtly misaligned like an orchestra with a drifting conductor. This is one of the most unsettling aspects of space weather. It can create problems that are not immediately obvious, not a dramatic failure but a creeping inconsistency. It is the kind of disruption that engineers fear because it is harder to diagnose. When a transformer explodes, you know where to look. When time slips by microseconds in one part of a network, the effects can cascade in ways that are difficult to trace. As the storm intensifies, the impacts start to climb from the delicate to the heavy. The headline fear, the one people imagine first, is the power grid, and it is true that geomagnetic storms can threaten grid stability. But power grids usually do not break first because they are not the most sensitive component. They are large, robust, and designed with many protections. They become vulnerable when storm-driven currents induce voltages along long conductors such as transmission lines. These geomagnetically induced currents can enter the grid and flow through transformers, driving them into saturation and causing heating harmonics and protective relay actions. In mild to moderate storms, grid operators may see increased reactive power demand and minor issues. In stronger storms, the stress can be significant, especially in high-latitude regions with long transmission lines and certain ground conductivity conditions. The danger is not that the entire grid instantly collapses. The danger is that a few critical components become overstressed. Protective systems respond, lines trip power, flows reroute, and the grid becomes less stable. If enough pieces trip in the wrong sequence, cascading outages become possible. The earliest grid-related issues might be increased alarms, unusual measurements, and preventive actions by operators. They might reduce load, postpone maintenance, adjust system configurations, or bring additional generation online for stability. These actions often prevent disaster, which is why many storms pass with far less drama than the most frightening scenarios suggest. But the watch exists because prevention requires preparation. You cannot protect what you do not anticipate. There are other infrastructures that can be affected as storms grow stronger, and some of them are surprising. Pipelines, for instance, can experience geomagnetically induced currents that interfere with corrosion monitoring systems. Rail systems can see signaling issues. Long undersea cables can experience disturbances not because the cable itself is being physically attacked by the sun, but because the Earth's electromagnetic environment is shifting. Even the atmosphere itself, when heated and disturbed, can change the conditions for radio propagation in ways that affect services far from where the aurora is visible. In a severe storm, auroras can expand to lower latitudes, and while that may produce stunning skies, it is also a marker that energetic processes are reaching farther into regions that normally remain quiet. If you want to know what breaks first in a way that feels concrete, imagine a timeline that begins with subtle warning signs and moves towards more consequential ones. First, specialized radio users notice fading and noise. Then GPS users in sensitive applications notice degraded accuracy or intermittent issues. Satellite operators notice increased drag-elevated risk and anomalies that require attention. Timing-dependent systems become more cautious. Aviation routes, especially polar routes, may be adjusted because high-latitude communication and radiation conditions can change during storms. Then if the storm is strong enough, grid operators start making protective moves, watching transformer health and tracking unusual currents. If the storm continues to intensify, localized outages become more plausible, not everywhere but in vulnerable regions, and not necessarily because the sun is powerful in a dramatic sense, but because the grid is a complex system where stability depends on many parts behaving within expected parameters. The phrase "what breaks first" can also be understood psychologically. The first thing to break may be the illusion that space is separate from daily life. We like to imagine the sun as a constant background, a warm lamp that rises and sets. But it is a dynamic star, and the Earth is not just a rock beneath it. Earth is an electrical system wrapped in magnetic lines connected to space by invisible currents. When solar energy couples into that system, the planet responds. The aurora is a visible signature of that response. The rest of it plays out in engineering logs, operator consoles, and the occasional odd glitch that reaches the public. A geomagnetic storm watch is a moment when those invisible connections become more active, when the space environment grows more volatile, and when the margin for error becomes thinner. It is not a guarantee of catastrophe. It is a notice that the risk has risen, and that the safest time to act is before anything has failed. In many cases, the most important story is not what breaks, but what does not break, because people took the warning seriously. Yet it is still worth understanding the weak points, because weak points define the shape of resilience. Signals break before steel. Accuracy breaks before power. Coordination breaks before comfort. The first cracks appear in systems that depend on stable propagation through the ionosphere and stable operation in low Earth orbit. And if the storm is strong enough, and if conditions align badly, the stress can push downward into the heaviest infrastructure. We have the grids that move energy across continents. By the time the public hears about a storm, the event is already in motion, already measurable, already approaching, or already interacting with Earth. The question becomes less about fear and more about readiness. What breaks first is usually what is most sensitive, most precise, most dependent on calm skies above the sky. And the fastest way to understand that is to remember that our most modern tools are built on something ancient and volatile: electromagnetic space, stretching from the sun to the Earth, invisible until the day it is not. Communication plans may shift. The system remains functional, but it carries more friction. Friction is another early break. It shows up as extra fuel, longer routes, altered schedules, and increased workload for operators. As the storm intensifies, the public begins to notice the most visible and often most celebrated effect: aurora. When charged particles travel along Earth's magnetic field lines into the upper atmosphere, they collide with atoms and molecules, causing them to emit light. Green and red hues can spread across the sky, sometimes visible far from the poles during strong events. The aurora is a visible trace of energy entering Earth's system. It is beautiful, and it can also be a warning sign that the geomagnetic environment is strongly disturbed. While people photograph the sky, engineers watch currents. One of the key pathways by which geomagnetic storms affect ground-based infrastructure is through geomagnetically induced currents. When the magnetic field around Earth changes rapidly, it can induce electric fields in the ground. Those electric fields can drive currents in long conductors, including power transmission lines. These currents are not the same as the alternating current that power grids are designed to carry. They can enter transformers and push them into undesirable operating regimes, causing heating saturation and harmonic distortions. In mild or moderate storms, grid operators may see increased reactive power demand and unusual readings. They may implement protective measures, adjusting system configurations and reducing stress. In stronger storms, the risk grows that transformers could overheat, that protective relays could trip lines, and that the grid could become unstable if multiple components respond in a cascading way. But it is important to understand the order of failure. Power grids are generally robust and heavily engineered. They do not tend to break first because they are not the most sensitive. They break later in the chain when the storm is strong enough and conditions align poorly. The phrase "what breaks first" points to a hierarchy. Signals break before hardware, precision breaks before power, confusion breaks before collapse. The first break is usually an invisible drift in the behavior of systems that assume the sky above is calm. Yet the power grid remains the most feared outcome, because when it is affected, the consequences can reach everyone. If a geomagnetic storm leads to significant grid disruptions, the effects can propagate into water systems, fuel distribution, heating and cooling, communications and emergency services, not because those systems are weak, but because they depend on electricity. The grid is an amplifier. When it is stressed, other systems feel the shock. Still, many storms pass without major outages because operators take warnings seriously. They have procedures. They have models. They have experience. A watch gives them time to prepare, to place staff, to monitor transformer temperatures, to manage load, and to coordinate with neighbouring networks. The existence of these preparations is one reason why the public may see less drama than the most frightening stories suggest. The watch is not a prophecy of disaster, it is a tool for reducing risk. To make this concrete, it helps to walk through a plausible timeline of a stormwatch event, not as a cinematic disaster, but as a sequence of small and medium stresses that may occur depending on the storm's strength. In the days before the arrival, solar observers detect an eruption on the sun. Coronagraph images show a cloud expanding outward. Models estimate its trajectory. Forecasters issue a watch because Earth appears to be in the path and conditions suggest a moderate to strong interaction is possible. During this period, satellite operators review their plans. They may delay sensitive maneuvers. They may check redundancy and fault protection settings. They may ensure that teams are ready to respond if anomalies occur. Power grid operators may increase monitoring and adjust operations to reduce vulnerability. Aviation and maritime services review space weather advisories. In the hours before arrival, upstream monitoring spacecraft to measure changes in the solar wind. The density increases, the speed rises, the magnetic field strengthens. Then the key moment arrives when the orientation of the magnetic field indicates whether the coupling with the Earth will be efficient. If the orientation is favourable, geomagnetic activity rises. In the first phase, high-frequency radio users begin noticing absorption and fading, particularly at high latitudes. Navigation receivers may show increased error or intermittent lock loss in some regions, especially where ionospheric disturbances are strongest. Satellite operators notice increased drag and may observe small anomalies in spacecraft charging or sensor behavior. Timing receivers may report increased noise, and systems may rely more on internal holdover. These are early breaks the world remains on, but it is less crisp. If the storm continues, aurora expands, the ionosphere becomes more disturbed. Scintillation may worsen. This can lead to more noticeable navigation issues and communication degradation in affected regions. Some satellite services may experience brief outages or degraded performance. As the magnetic variations continue, geomagnetically induced currents become more significant. Power grids in vulnerable regions may see increased reactive power demand and potential transformer heating. Operators may implement further protective actions. In the worst aligned scenarios, a few components might trip, causing localized outages or the need for rerouting power flows. Whether that becomes a large cascade depends on many factors, including storm intensity, grid topology, ground conductivity, and operational responses. This is why storm watches do not always translate to public disruption. The watch is about readiness in a system full of branches. Now consider the phrase here as what breaks first in another way. It can be tempting to rank vulnerabilities purely by drama, to assume the first break is the biggest. But the first break is usually the least dramatic because it occurs where precision is highest and margins are smallest. A modern society is threaded together by invisible agreements about time and signal integrity. The global positioning system is a web of clocks in orbit. Telecommunications rely on synchronized timing. Data networks depend on precise coordination. Navigation depends on stable propagation. When the ionosphere becomes turbulent, it does not smash a device like a hammer. It slightly bends the path of a radio wave. It slightly changes the delay. It makes a receiver work harder. It increases the odds of a dropped lock, a temporary outage, a moment of uncertainty. Those moments are the first cracks. They are the earliest signs that the environment has become noisier than the system expects. From that noise, bigger disruptions can grow, not because the noise is loud in a human sense, but because many systems are coupled. A small timing error can produce a larger coordination error. A dropped navigation lock can trigger a fallback mode that changes operations. A satellite entering safe mode can interrupt a service that other systems depend on. A communication degradation can slow the dissemination of information exactly when information is most needed. This is how complex systems behave under stress. They do not fail at the strongest point, they fail at the seams. It is also helpful to distinguish between the kinds of harm a geomagnetic storm can cause. Some effects are transient. A radio blackout can last minutes to hours. Navigation accuracy can degrade and then recover. Satellites can ride out increased drag and return to normal operations. Other effects can be cumulative. Increased drag can consume propellant over time. Repeated storms can age hardware. Transformer heating can cause wear and, in severe cases, permanent damage. Yet the majority of storms do not produce the worst outcomes, and it is important not to let fear outrun reality. A storm watch indicates elevated risk, not certain catastrophe. The calm truth is that space weather is part of the environment and modern society is learning how to live inside it. There is a reason that forecasters use structured scales and cautious language. They know the uncertainties. They know that the strength of the coupling depends on magnetic orientation that can be difficult to predict precisely until the solar wind is measured close to Earth. They know that regional effects vary with geography and infrastructure. What can be said with confidence is the pattern. The upper atmosphere responds quickly. Radio propagation becomes less reliable. Navigation and timing become less precise. Satellites experience increased drag and risk. And if the storm is strong, long conductors on Earth can carry induced currents that stress power systems. That pattern tells the story of what breaks first and what breaks later. It is also worth noticing why geomagnetic storm watches feel more relevant now than they might have decades ago. The world has built more of itself into space and into the upper atmosphere's quiet assumptions. Satellite constellations have multiplied. Navigation has become a default layer for phones, cars, ships, and logistics. Precise timing has become a silent backbone for networks. Power grids have become more interconnected, which improves efficiency, but can also create pathways for cascading effects. The modern world has gained capability by tightening its tolerances, by pushing efficiency, by reducing buffers. Efficiency is not a moral failing. It is a design choice, but a design choice has consequences under rare stress. When a geomagnetic storm arrives, the environment pushes on those tolerances. The first breaks appear where the tolerances are narrowest. There is a quiet lesson here about resilience. Resilience is not only about resisting the biggest threat, it is about maintaining function under a spectrum of stress, from subtle to severe. A system that can handle a minor loss of signal gracefully will fare better than one that assumes perfection. A network that can hold accurate time even when satellite reception is intermittent will fare better than one that relies on a single source. A grid that can monitor induced currents and adjust operations will fare better than one that runs close to limits with little situational awareness. A geomagnetic storm watch is in a way a reminder that resilience begins before the storm in design, in preparation and in humility about the environment. The sun is not an enemy. It is a star doing what stars do. It cycles through periods of higher and lower activity. It releases flares and ejections. It sends fast and slow streams of solar wind. Earth has endured this for billions of years. What is new is the presence of delicate, precise, electrically sensitive systems spread across the planet and in orbit. The storm is the same kind of phenomenon it has always been. The vulnerability has changed. This is why the question here is what breaks first is not really about doom. It is about interface points. It is about where human engineering touches the sky. The ionosphere is one interface point. The magnetosphere is another. Long power lines are another. Satellites are another. Wherever the interface is thin and the margin is small, the first breaks appear. Even the language of watch is telling. A watch does not mean an event is happening everywhere. It means conditions are favourable. It means attention should sharpen. It means operators should prepare. It means the public should be aware without panic. In a healthy information ecosystem, a watch would be met with calm readiness. Grid operators would implement procedures. Satellite operators would monitor. Aviation services would adjust as needed. Researchers would collect data because storms are also opportunities to understand the system better. For many people, the most visible sign might be nothing at all, or perhaps aurora at an unusual latitude, or a brief navigation oddity, or a moment when a radio station fades strangely. These are small windows into a larger physics event unfolding overhead. It is comforting in a quiet way to recognize that much of the world's safety comes from people who treat these warnings seriously, people whose work is rarely celebrated because success looks like normalcy. A power grid operator preventing a cascade produces no viral clip. A satellite team keeping a constellation stable produces no dramatic footage. A navigation engineer designing receivers that handle scintillation gracefully produces no headlines. And yet these are the structures that keep the first breaks from becoming the later ones. To keep the story grounded, it is useful to summarize the likely order, again, not as a list on a screen, but as a simple unfolding. When the watch is issued and the storm arrives, the upper atmosphere is disturbed. Radio propagation becomes less reliable, especially for high-frequency communication and certain satellite links. Navigation accuracy can degrade due to ionospheric turbulence and scintillation. Timing systems that rely on satellite signals may experience increased noise and may depend on redundancy. Satellites in low Earth orbit experience increased drag and elevated risk of anomalies leading to protective operational changes and occasional brief service interruptions. Only after these and primarily in stronger storms do induced currents in long conductors become a significant threat to power grids and other infrastructure. In that later phase, the consequences can be more broadly felt, but even then, outcomes vary by region and by preparedness. The first breaks are therefore often the least visible, occurring in the intangible layer of signals and timing that modern life quietly assumes. There is a final gentle thought to rest with. The sky above the sky is not empty. It is structured, flowing, and alive with electromagnetic motion. Earth is not peeled off from that motion. Earth is connected by field lines, by currents, by particle streams. A geomagnetic storm watch is a message that the connection is about to grow more energetic, that the hidden weather of space is becoming more active. The earliest failures happen where human systems are most sensitive to that activity in the pathways of radio waves, in the precision of timing, in the stability of satellite orbits. And if the storm is strong enough, the stress can reach down into the heavy infrastructure of the ground, into the grids that carry energy over long distances. Yet most of the time the story ends without catastrophe, not because the storm was imaginary, but because awareness and preparation absorb the shock. The watch is the first step in that absorption. It is a quiet invitation to respect the environment and to remember that even in an age of technology, the sun still sets the conditions of the space around Earth. And as the world turns beneath a sky that may glow with distant aurora, the planet continues to move through the solar wind carried forward inside its magnetic shield, while human systems listen closely for the faint early cracks and do their best to keep them from widening into anything more.